So, so welcome to Operation Research 2. Okay, so today's topic is about IFN, so Ideal Flow Network. So this is basically my research. Okay, you can check in Lentera. So I updated this morning lecture, and then this is the slide, and you can also download the Excel add-ins, yeah, if you want to. This is not available in the website. In the website of Revolut, only version 2. This is version 7, so you can download that. Okay. To install it, just double click the add-ins. Okay, or you can check the manual. I think this is the manual. So you just double click the idealflow.xlam. Okay, and then you can also put in this folder. Okay, this is the Excel folder. Okay. So if you install this, and then you go to the file options, okay, and then add-ins, and then you add the add-ins, and then you click the Ideal Flow Network, and then you can just click OK. So if correct, then you will have that menu. If you do a right click, you have a menu. Okay, let me check the Excel. So if you are correct, you installed already. Okay, down here you will have a menu of Ideal Flow Network. Okay, so what is this? Okay, what is IFN and what are the properties? And mostly I will just, because this is just introduction, so I will discuss more on application, examples. This is something that you like probably. Okay, you have learned about Markov chain, right? A while ago. So if Markov chain is about simplified dynamic rules, yeah, on Earth, so IFN is about ideal rule in heaven. That means this is not dynamic. Okay, it's a steady state. So similar to the queuing theory that last time you discussed. Okay, so the formula of queuing theory is based on the steady state formula, right? So the long-term view. Okay, similarly, when you have irreducible Markov chain, regardless whether they are periodic or aperiodic, so that will become IFN. So what is IFN? Is a steady state relative flow distribution, so in a strongly connected network, where the flow are conserved. So in essence, okay, IFN is basically irreducible Prima-chain. So of course, because this is basically the steady state of Markov chain, okay, you can also use matrix or network, as the graph. So again, there is a strong assumption, okay, in IFN. Okay, the decision on each node of IFN is following Markov properties. That means it's local information rather than the global information. So for each node, you need to decide based on that local information. Okay, not the entire network as global information, but only on that node. Okay. So IFN can be used in many applications. Different. You can see the slide. Okay, I put a lot of different example application. So why it can be defined, can be applied in many applications is because the flow is undefined. Okay, the flow is undefined. So you can see IFN, okay, check the effect, the long-term effect, yeah, or the long-term view of a system. Okay. Then you define the flow, okay, in your context of application. Okay. So as I mentioned earlier, that by definition, okay, IFN is practically irreducible premagic. Yeah. So if you want to apply this, that means you need to understand the interpretation of irreducible, right? So what is irreducible? So irreducible basically means unity. Okay. So a system being irreducible means you can see the part as integrated with the whole. Yeah? So philosophically, when you start to see things still unconnected, that means your view is still partial view. Yeah? So when you use unified view, integrated approach, okay, then everything in our system are strongly connected. Okay? Then of course with that kind of system, you can say, okay, this is irreducible. Do you get it? So when you want to apply IFN, check two things, yeah? Whether it is irreducible or not. Second is whether it is premagic or not. So irreducible means integrated. Yeah? So all the part that I put into color here, that's the meaning of interpretation of irreducible. Yeah? Second is premagic. Yeah? Whether your system is premagic or not. What is the meaning of premagic? Yeah? Balance, equilibrium, stability, or steady state. Yeah? So premagic can be viewed as flow preservation, energy preservation, or entropy preservation, or whatever preservation in the weight system. Yeah? So if you think philosophically, IFN represent equality, justice, fairness. Okay? So when you have a system that have a give and take, yeah, so that balance can be modeled using IFN. Similarly, if you have right and duties, yeah, or responsibility that creating an equilibrium, then you can again use IFN to model. You get the idea? So premagic, irreducible. Yeah? Irreducible means whole, unity, unified. Okay? Premagic means balance or equilibrium. Okay? So if you can have these two, then you can model using IFN. Okay. So otherwise, of course, this is not panacea, so you cannot model using IFN. Okay, so I have developed over several years. Okay, so Python you can check in GitHub, also XLR actually the version 2 is in my website, but version 7 is already in Lentera. Okay, and I also have the online HTML using PHP and JavaScript, and I also developed the MATLAB version. So let's see for a while that. So if you type my name, so GitHub Teknomo, so you can see there are actually two. Yeah. One is the GitHub itself, and then IFN Transport and Ideal Flow Network. So yeah, I have many free open source model here. So one of them is Ideal Flow Network. So you can do a pip install Ideal Flow Network in your Anaconda Pro, for example. Then you can have IFN inside your computer. Yeah. So this is the example that you can just copy and paste. Okay. The tutorial. There are also many scientific papers that I have published since 2015. Yeah. Okay. So and for the transportation application, okay, you can also go to this GitHub Teknomo /IFN Transport. Okay, so if you want to copy, you copy the whole thing. Yeah, you just copy the whole thing and then put into your. So you don't need to install here. You just copy the whole code into local folder. Okay, and when you run using Python, okay, main.py, so you will have like this, and from here you can download the roadmap data. Okay, and say for example Surabaya here, you specify the, you can put the city name, and then and then you click get boundary, it will give you the boundary of the city, or you can specify your coordinate, yeah, of the longitude and latitude. Okay, and then what type of road, for example, and this is the automatic data cleaning, and the file name that it will give, and then you just download the map. Yeah. It will automatically download any city, yeah, in the world that has in OpenStreetMap. Yeah. OSM is OpenStreetMap. Once, if otherwise, you can go to OSM website, yeah, OpenStreetMap website, and then you can check. Okay, you can zoom in and zoom out, and then to get the this coordinate. Okay, so if you go directly in OpenStreetMap website, you will get XML like this. Yeah, so you can download there also, but this is what you will get. So when using the IFN transport, you will get a better format. Okay, so it's a table with the node and capacity, distance, maximum speed, okay, number of lanes, road width, and type. Say for example, this one is the example. Okay, so these are the, and also have some node data that you can check. And then this is the example of network when you download. This is near Petra. Okay, this is Ahmad Yani. Okay, and if you zoom in, you can see the actual network here. Okay. So you can even zoom further to check. Okay. And then from there you can define some scenario. So for example, using the base scenario, mean the existing, right? So then you can set, for example, using truffle model. Okay, I can run this. Okay, so when you define the scenario, you can create. So you can set the browser, okay, which folder you want to do, and then if there is an existing scenario or not. Okay. After that, you can set the model. There are two models here. Okay. Using GreenShield, you will create a congestion maximum 1. Using BPR, your congestion can be more than 1. Yeah. And then if you have a cloud node, you can check here. Okay. Otherwise, no need. And then this is the one that you can calibrate, yeah, based on the real flow, or based on the total flow, or based on maximum congestion. Yeah. So, for example, if you use the real flow, then you need to define the real flow. Yeah. If you use the total flow, okay, you put the total flow there. After that, you can define the scenario. Yeah, click this, and then you run the scenario. Okay. So once you run the scenario, okay, you will get this result. At this point, you will also get the flow. Yeah? So you can also get the real flow, and then it will find the optimization to calibrate your model with the real world data. Okay, this is the, and from there you can get the actual flow for each road. So what is it useful? Say you have a road network, say for example, Ibu Kota Negara. Yeah? So there is no real road there, right? Only on the map. So if you can set that map into this IFN transport, okay, it will compute directly, and then it will give you which road is actually congested, which road is not. And you can also simulate, for example, oh, if this is congested, what will happen if I change the number of lane in here and there? Okay, so that you can play around to solve traffic congestion problem. So this is one of the application. So basically, this is Markov chain, or regular Markov chain. Okay. Other example. Okay, so if you go to my website in Revoledu tutorial IFN, okay, so you can also see this is not yet really finished, but I just make a few. Okay, you can also have. So this is the capacity matrix. You can calculate. You can see the result. And one thing I want to show you, this is the transport a while ago, which is in IFN transport in GitHub. Now I put it into JavaScript so that you can also input it directly here and compute. Yeah? So you just compute, you will get the result. Yeah, how many congestion in the network, and then you can get the actual flow and congestion level here. Okay, so you can get directly, including the speed, yeah, and delay and travel time for each link, and the probability and stochastic. So next, I want to show you also the application of IFN in music. You can probably visit this website. You can try it on your own. Okay, so here I play. You can select sample music. Okay, so I just make, say, this one. Yeah, that is Mary Has a Little Lamb. You know that song, right? Kindergarten song. Okay, so and this is the actual. So yeah, that one. This is the code basically of Mary Has Little Lamb. Okay, and now I can, when you click this button, okay, there is an IFN inside. We learn from this code, and then from there it will generate new music. So computer can generate music now using IFN. Cool, right? So I can generate, okay, and uh, okay. If you notice, the song generated by IFN is similar to the one that we give as training, right? So the only difference is you can now generate different type of music that you want. Still similar to Mali F Little Lamb, correct? Have similarity to Mali F Little Lamb because it generates based on the one that we train. Now let's try another song. For example, Mozart. Okay, and then we train that. Okay, so so IFN is basically an AI, yeah, artificial intelligence in this case. Okay, because whatever you put in as the training data, they will produce another song in this case. Okay, it is similar to the one that you train. Any comment? Okay, so let me let me show you another one, which probably give you better idea. Okay, so this I will close this. Yeah? So this is another IFN that I created. Okay. Okay, so this is the demo of IFN for machine learning. Okay, again, you know we can do a table processing. Okay, so this is an example of table. Okay, so you can say I load this table. Okay, so this is the table of data, right? And then this is the class. Yeah? My computer is the class. Whether for different age, different income, different status, whether they are student or not, what is the grading rating, and then whether they will buy computer or not. And we can train. Okay, this is the parameter. Markov order is the parameter. You can train. So, right. So you can see when you train, you will get the IFN for each of the class. Right. So yes mean by computer. Okay, no mean not by computer. And this is the hash code of the data that I put inside. And these are the flow. Okay, these are the flow. The one in red is the flow. Okay, and with that, once you train, you can now put new instance of data, example, and then you can predict. So, oh, the prediction is no with certain confidence level. Okay. Similarly, we can say, for example, this one is transportation no. So this is the data with a tree, right? Whether they will, okay, this is the gender, car ownership, travel cost, income level, okay, and then whether they will use bus, train, or car, right? So, and when you train, okay, 100% precision, and these are the IFN trained based on that data. Okay. Again, this is, if you look at the network is always irreducible and always pragmatic. Yeah? The number of flow in is equal to the number of flow out, always. Okay? Irreducible pragmatic. Okay, so here you see the number of flow in is 1 and 1. This is out is 2, right? It's always that. And then with that you can predict. Yeah? So you have certain data, and then you predict, and then every prediction you can get certain confidence level. And not only that, of course, prediction you have many machine learning can do, right? So the one that make and unique is actually you can generate. Yeah? Not only predict, you can generate for certain class. For example, I want to use car. Who use car? Okay, or mostly is female. Yeah, with have car ownership 1, and then travel expenses expensive and high. You can generate different data. Yeah? So with this you can practically this is the inverse. Yeah? You give a training, okay, but if you look at the result here, this is not probably not even there. Okay, so the one in used car, expensive car ownership 1, right? Amphibia, this is still there, but you can check that not always there. Yeah, the one that practically the IFN can generalize. Okay, the one that you already trained. So there is some kind of intelligence inside. Similarly, we can also do image processing. So this is the one that I trained. So this is the picture. We just click here. Okay, I just make very simple GUI. Yeah, and then we put the label. Yeah? Put the label here. Okay, or I can also draw. Yeah, I can clear the picture. I can create a random drawing, right? And then I can draw that. So okay. This is the one that I already trained. So this is, I said this is E, right? This is E again. This is E again. So different E. Yeah, I put it different scale also. This is A and so on. And then we can train. Yeah? We can train one shot for one, or we can optimize. Yeah? So now when we optimize this, it will produce some parameter data with accuracy 100. With that, now you can see prediction. Yeah? So when you say, okay, when I have A like this, predict it will, the prediction is A with 100% correct. Yeah? So what happens, this is F, right? Suppose, let's predict here. Oh, this is F, correct. Yeah? So IFN can predict, okay, the label. Okay? Of course, we can train that. So this is another application of image processing, right? Okay, and this is a cool one. So this is the prayer. It's in Indonesian, so to show. And this is okay. This is the book okay, of Coping Hope, again in Indonesian. Okay, and we can if I load this option. Okay, so sorry. See, I have this one. If I load this one, okay, so I loaded this, and I can generate. So you can, okay, I can generate how many sentences I want. So I can generate. Basically, IFN can create text, can create story. Okay, if I train with using a poem, okay, say I have this poem, I load this, so IFN can also create poem. Okay, so if I train using some greetings, okay, again it will give some greetings. Okay, so the one that you train, again, if you train using prayer, where is the prayer here? Okay, so I load this. So you can generate the prayer, okay, or you can check whether this is actually this, what kind of prayer is this? Yeah? So you can predict, oh, this is Tanda Salib, okay. So you can also put the label here to predict. Yeah? So you can type what is the prayer. Oh, so you can practically you can put any text, okay, and then you can categorize. For example, oh, this is the letter from Paul, and then this is the letter from Peter, and you train that, okay, and then now you have a new letter, right, and then IFN can predict, okay, which letter it is. Okay. So, okay, so far, is there any question? No question, yeah? Okay, so let's go to the detail now. Okay, that is to lure you. Okay, with certain applications. So let's go to the detail. So how we will calculate the IFN, okay? So IFN can be computed manually if it is very small network like this. So here is an example of small network with only 5 nodes. You see, I have 1, 2, 3, 4, 5, and this connection I put. So what happened is, say, I assume certain probability distribution, right, for each node. So let's assume this is equal, yeah, for this example, I assume equal. So I just put 100 here, okay, because they are equal, so I put 50-50, right? And you see, so from here 50, I divide by 2, so become 25, okay, and then this one again divide by 2, become 12.5, right? And then what happened is here you can continue, right? So this is already IFN because you can check here, okay, the sum in node 5, okay, 50 plus 25, 12.5 is exactly the same as 100. So this is already IFN. Okay, you can also make it integer, yeah, because this is relative flow, so you can scale up and down. Okay, so to make it integer here, I just divide by the minimum, yeah, so I get 1 in here. So this is 8, right? So this is the standard, yeah, that we can use. Right. So you can manually, you can, amazing part here is you can throw any network, okay, and then you can, as long as they are irreducible, okay, you will get IFN. Amazing. Okay. Okay, if you want to use Markov chain, you can also use this. Okay, until here you already know, right? This is the one that we discussed in Markov chain, right? So IFN is just, this is additional formula that I created. Yeah, so you just multiply this with J, and then this is the Hartman product, so element wise with the S, you get F. So my contribution is practically very small, only this one. Okay. Because this is an OR, so operation result, right? So we need to ask, what is the optimization here? Okay, so let's define. So this is the transition matrix of the Markov, right? And then you take the ln, okay, multiply by itself. What is this? This is entropy, right? Okay, so this is the node entropy for each node, okay? And let's say the phi a while ago, okay, for each node I, okay, and if you sum all of that, let's call this kappa as total flow, okay? And from here you can see if I take the Vi divided by kappa, that means its node value, okay, its node value I divide by the total flow, and then I multiply with this node entropy. So I will get a new network entropy. So this is conditional entropy. Yeah. So this is the one that we use to optimize. Yeah. So here, so we want to find the phi I. Okay, maximizing the entropy. Okay, subject to constraint that of course must be stochastic, right? Yeah, the value must be stochastic, and then this must be premagic. Yeah? So S tan phi, S tan phi. This must be premagic, and then the total flow must be kappa. This is the one that we set as parameter. Yeah? Kappa is up to you to decide. Okay, so using this, you can also use Excel. Okay, so suppose this is your stochastic matrix. Okay, and you can calculate the entropy out of this. Right? Last time you already practiced maximum entropy. Right? So you just get each of these. So if this is 0, so you set as 0, and then you sum all of this, become entropy. And then now you want to maximize this entropy, okay, subject to this row sum equal to that row sum as column sum. This is the row sum, this is the column sum, right? And then subject to, again, the kappa, okay, must be the same as this one. When you use solver, you will get the ideal flow. Yeah? So you see the ideal flow, of course, will be premagic. What's the meaning of premagic here? You see the row sum is exactly the same as column sum. Okay, so I can just put that. Okay. Okay. The network must be irreducible, clearly. Yeah. So now if you use Excel, okay, so I have Excel here, okay, and oh, you want to try? You try to open that FN Excel add-ins. So let's try that. Okay, so I will create here. When you put n underscore, okay, these are the menu. Okay, equal n underscore. These are the menu for FN Excel add-ins. Or I created many functions. Yeah, that you can use. Yeah. So let's create a random capacity matrix. Okay, so random capacity. Okay, so I just put like this. So now you can put any size. For example, how many you want? Let's make 4. Yeah? Okay, so you just highlight this. Okay, and then what you will do, you, as the usual, this is a matrix, so you press F2, right? And then Shift Control Enter. Yeah? So you can create a random capacity matrix. Yeah? So I put C here, yeah? Capacity matrix. Okay, so let's name it A, B, C, D. Oh, C. Yeah, and this is also A, B, C, D, right? So this is basically just random, irreducible, okay, matrix. So if you want to check, okay, is irreducible, right? So you want to check that, we can put equal and underscore is. Yeah. So you can have is ideal flow, is non, is pragmatic, and so on, is symmetric. So this one I will use is irreducible. So tab, okay. So this one, right? Or maybe yeah, true. Yeah, always. So you can keep name if you want. So let us keep name. So I will open this. Okay, I will name this capacity. Okay. So it's reducible, yes. Right? Okay, so yeah. Is pragmatic? Check, yeah. N underscore is pragmatic? No. This is not pragmatic. Yeah, false. Right. So this is just random capacity matrix. That means just any flow that you can put there. Okay, this is not ideal flow yet. So if you want to get the ideal flow network, okay, let me copy here. Right. Just copy here. So I'll keep name flow. Right. So let me put different color. So let's put it as orange. Okay. So of course now you need to change the formula. Right? N underscore, yeah. So capacity to ideal flow. Yeah? So capacity to ideal flow. You can get that, right? Okay, let's put it this way. Close. Okay, and then you highlight everything. F2, right? Shift Control Enter. Yeah? Oh, you get that. Okay. When you run this, okay, F9, you can get the different random capacity and random ideal flow. Okay? So check the sum. Okay? Let's check the sum. Whether this is pragmatic or not. Yeah? You can check. So just sum. Okay? Right, so sum of the top here. Okay, so you can see that this is always pragmatic. Okay? So now again, of course, when your capacity matrix is irreducible, okay, it is always okay. Let's keep name first. This is, let's keep name this as flow. Okay. Okay, so this matrix has flow. So let's check N is irreducible of this flow, right? True. Yeah. And then check again. N underscore is pragmatic, right? So this flow always, yeah. You can see it. So this is 19, 10, 19, 19. This is 19, 10, 19, 19. Yeah. Okay. So you can also use the same like this, but now you can set the kappa. Yeah? You can also do the same thing, but at this point you set the kappa. So I will put kappa here. Kappa is the total flow, right? So this one is yellow, meaning you input this. So I will put, I want to say 100. Okay, so I delete this. So again, N underscore, yeah, capacity to ideal flow of capacity, right? Okay, but this time you add the parameter kappa. So this one. Okay. Okay, and then what you will do, F2, Shift, Control, Enter. Okay, this is exactly just the scaling of the. This is the standard form, right? So this is the one that the total is 100. Okay, so if you change this, for example, total is 200, it will change. Total is 200. Yeah. So every time you move, okay, of course it will, because it's random, so you can generate different random value. But again, yeah, they are all pragmatic. Yeah, you can see, and the total is the one that you specify. Clear? Okay. Of course, I can create a drawing. Yeah? If you want, I can create a drawing. So this is the node, right? So I can put X and Y here. Okay, so I can put any any value. So yeah, I can just copy this 100, 100. Okay, and you can now draw. So say n underscore draw network. Okay? So draw network, the one that you draw is the flow, and then you need to put the coordinate, including the node name. Yeah. So can you see that? And when you click this, okay, enter, you will get the drawing. Now you can just change the value. Okay, so say I have 200, for example. Okay, so here is 50. Here is 150, maybe. And then here I can give different value. Say this is 500. This is 350, and this is say 250. Yeah, so you can create a drawing directly there. Okay, and of course, because this is random, so every time you change, it will also create a different network. Okay, so at least this is how you get from any capacity matrix to ideal flow matrix. Yeah? And of course, if you divide the flow divided by the capacity, you will get congestion up to the scale. Yeah. Okay, so you don't need to use the solver because there is add-ins already, so you can create on your own. Clear, yeah? So these are the properties that you can see clearly. Yeah, must be strongly connected. Yeah? Strongly connected network, right? And then must be pragmatic. That means the sum of row k must be the same as sum of the column k. Yeah? Optionally, later I will discuss, is you say your network is not strongly connected. Right, that's often happen, right? What happens if my network is not strongly connected? Can I still use IFN? Yes. Okay, you can still use IFN, and as long as your network is not unconnected. If you have two networks, you cannot. Yeah? But it's only weakly connected, means you have sink node, you have source node, or component, you can still use. Yeah? How to do that? You create this is again optional modeling tool, so you can introduce cloud node. In fact, this is what I use for the machine learning a while ago. Yeah? So we create a cloud node, okay, to connect what we connect. We connect the sink node, yeah, to the source node via cloud node. Yeah? You only need one cloud node. Yeah? You only need one cloud node. With that, it will become strongly connected. Yeah? And then that result you can hide later. Yeah? And another property, if you can check the scaling, right? Because ideal flow is basically relative flow. Okay, so because they are relative flow, you can always, it is always a rational number. Okay, rational number, you remember? Something divided by something. Okay, so in that case, you can always make it into integer. Okay, and two IFN are called equivalent. Okay, if they are just scale, positive scale to each other. Okay, so again, what is the meaning of irreducible? Okay, strongly connected, right? So from any origin node, yeah, you can go to any other destination node, and don't forget this and, okay, you can go back home. Yeah. So transportation system is of course strongly connected, right? Otherwise you can go somewhere and then you cannot go home. That is not okay. So transportation network is always strongly connected. Okay, communication network is also strongly connected. Yeah. So again, if you want to use IFN, you need to understand the meaning. That means these are the interpretation. Yeah? Unified view, integrated approach, connected, and so on. Yeah? And this is the example of reducible, right? Weakly connected, yeah, with some component here. Okay, so yeah, I think we already practiced this. This is strongly connected or not? Can you see?
Oh no,
No.
because
Why?
F and E, once you go in, you can never go out.
Yes. So there is an absorbing class here, yeah, final class here, right? So once you enter here, you cannot go out. Okay. So then, how to do that? You can connect this to the source. Yeah. Yeah. So this is absorbing class. Okay, so again, how to test whether it is irreducible or not, right? So to test whether it is irreducible or not, you know we can add with identity matrix, right? Yeah, this is adjacency matrix, yeah? And then exponent with n minus 1. Like a while ago, we already discussed this during Markov chain, right? And then now adjacency matrix is reducible. Remember, we also discussed this during the absorbing Markov chain. Yeah? Okay. You always have 0 here. Okay. A while ago, I put it up here. It's the same thing, right? So you can multiply with any permutation matrix, okay, so that you will get this form. Okay. So okay. So this one you can put into matrix. I think it's easy. Right? Okay. Here you cannot see, okay, whether it is reducible or not, especially when your network is very big, so you cannot see that. Then you need to test, yeah, using that matrix. So if you put this up to 5, because this is n minus 1, that is 6 node, okay, and you can see there is still 0. Yeah? There is still 0, so that means this is reducible. Exact form of this one. Yeah. So this is not. So this is the same thing. Oh, how about this one? This is irreducible or reducible? There are 2 components here. This one is component. This is another component. And then from one component you can go to the other. So the whole network is irreducible. Yeah? Okay, and you can see if you put I plus A, okay, now become all positive. Yeah? You can see all positive. Okay, yeah. So this one is clearly reducible. Okay, and you can see if you put I plus A exponent 5, again there are some zeros. So this is reducible because this still contains 0. Okay, the pattern of 0 is important. Okay, now premagic means the sum of inflow is equal to the sum of outflow. Amazingly, if you have a irreducible matrix, okay, when you run this, always you will get premagic. Always. Yeah, this is the one that I feel, very nice. Okay, so again, these are the, the, the sum of inflow is equal to the sum of outflow. Okay, so amazingly, if you have a irreducible matrix, okay, when you run this, always you will get premagic. Yeah, this is the one that I feel very nice. Okay, so again, these are the, the sum of inflow is equal to the sum of outflow. Okay, so again, these are the interpretation, yeah, of pragmatic here, yeah? Balance, steady state, preservation, equality, justice, fairness. Yeah? So based on this interpretation, then you can apply. Okay. Now, a while ago I said, okay, you need a cloud node probably optionally if you want to connect, yeah? Weakly connected to become strongly connected. Yeah? So my theorem said that only one cloud node is sufficient. Yeah? So again, this is an optional modeling tool. Okay? What does cloud node mean? Cloud node means external environment outside your system. Okay, so this is to make weakly connected into strongly connected. Yeah? So of course you can hide later after the computation. Okay, so now here it is. If you have weakly connected network, okay, so first reveal that the cloud node to make the strongly connected network, and then you can get the ideal flow matrix. Okay, and then you can calculate everything else, and then you can hide that value. Yeah? So IFN can only be computed using strongly connected network. This is, I repeat again and again. I give this lecture to many, okay, and they make the same mistake again and again. What is the mistake? They always forget that the network must be strongly connected. Okay, so okay, I give this to the Indian student, for example, and again they said, okay, why this is not, why error? They said, I put into the program, why error? Did you check if it is irreducible or not? Okay, okay, still have weakly connected, so that's why it's error. Okay, you must first check whether the network is irreducible or not. Okay, if not, you need to create a cloud node, okay, to connect. Okay, so very important. Okay, so how you connect that cloud node? Yeah? So this is example of very simple weakly connected, right? So you have the source here, you have the what is this? The sink node, yeah, the tooth sink node. Okay, then you can just add this. Yeah, this is the cloud node, right? So you just connect the sink into the cloud, and then from the cloud to the source. You see? Yeah. So you see, this is 2. Oh, I think I made mistake here. This must be 2. Yeah, it must be 2 because the sum must be the same. Yeah, yeah, I made mistake in that drawing. This must be 2, not 1. Yeah. Oh, okay. This is 1 and 1. Okay, that is correct. Yeah, this must be 2. Okay, so after that you can hide. Yeah? So once you hide, you can get this value with this. Actually, it is computed based on the cloud node. Or even if without cloud node, you can directly connect, yeah? the source to the sink to the source. Okay, you will get exactly the same. Yeah? Without the cloud node, you can also use the same thing. Clear? Clear, clear, clear. Okay. So here in this example, okay, this is actually already irreducible. Okay, if you look at this is already irreducible. Yeah? But I still add cloud node here. Why? Because this is represent an intersection, right? And this represent an external environment. Okay, so I add this. Why? Because the flow that coming to this intersection actually don't come from here, but come from outside source, and then it will go to outside environment. Okay, so again, the cloud node here represent the external system. Okay, it's already irreducible, but we still add the cloud node. Clear, yeah? This is a modeling tool. So, and how are you going to get this is the capacity matrix, right? So how are you going to do the capacity in this dummy link? You just continue, yeah? So if this is 1, then continue 1. If this is 3, then continue 3. The same thing here. 2, continue 2. Just continue all the flow or the capacity that you have. Is it clear? So okay, let's practice so that become clearer. So can you? This is clearly source, right? And this sink. So can you add cloud node and dummy link? So if you put this one 2, 3, 4, 5, for example, any flow that you put here, can you put also the flow in the dummy link? So in this case, all you need to do is just connect okay, to the cloud node. Okay, so the sink go to the cloud node, and then from the cloud node go to the source. Okay. So example, I guess I just put number here so that you can see. So I put here any flow, right? So I can put 2, here I put 3, here I can put 4, and then here is 5. So then you just continue, yeah? This must be also 5, right? This must be, oh no, 5 plus 3, how much? 8, yeah? Correct? This must be 8, and then 2 plus 4, that means this is 6. So inside that cloud node, I have 14 here, okay? And then, how much is here? This will become 5, right? And then this one will become 9, correct? Clear, clear. Easy, yeah? Yeah. So easy because you can see, now if you want to know the node value, okay, what is the node value in node 2? Of course, this is 9, yeah? Inside this node. How about node 4? What is the node value in node 4? Yeah? 3 plus 5, yeah? This must be 8 inside here, right? How about the node value in node 3? 2 plus 4, so this must be 6, yeah? Correct? How about node value in node 1? 5, okay? 2 plus 3. So the sum in equal to sum out. Total flow in equal to total flow out. That is the node value. Is it clear or not? Super, super. Okay. So I think we stop until here first. Okay. You can practice this. Okay, if you want. So you can practice this. Okay. So I have. Okay. You can add. If you look at this is not. See, the sum of A is 100. Okay, sum here, right? The sum is 100. Okay, this is 200, right? In here is 0, 0. In here is 300, right? And then the sum here is 0, 0, right? So now if you add cloud node, okay, if you add cloud node, okay, so I can add cloud node Z. Magically, when you add cloud node Z, what will happen? It suddenly become pre-magic. Can you see? Wow. Right? Cool, right? Okay. Yeah. Suddenly become pre-magic. Yeah. So, okay. Okay. So you can clearly see. Okay, the original is not premagic. Okay, but why? Because actually this is not, this is reducible, right? So once you make it irreducible, suddenly become premagic. So again, you don't need to do the Markov chain because it's already computed. All of these are steady state, okay, of irreducible Markov chain. Yeah. Okay, very nice. Okay, so up to here, next week we can go to the detail and more application, yeah, of this. Okay, thank you very much for today.
Okay. Thank you, sir. See you next week.
Yes, next week. Next week you will